is half-life. And half-life is exactly what it says. It's the time needed to end up with half of the material you started with. And this becomes very important, especially in science, when they were working with the atomic bomb and such. They used materials that were radioactive, and so they would calculate their half-life, and that's how they knew what would be going on with those materials. So half-life. And just like half-life, doubling time, same kind of thing, but in reverse. It's the time needed to double a substance you start with. So I say substance, but it could also be money. So like, for example, maybe you want to invest your money. You've got $100 and you say, well, how long will it take me to double my money? Exponential functions look like some number to the power of x. For example, you could have something like 2 to the x is your function. And the big idea here is that the variable is the exponent. And if you were graphing this thing, you would see that exponentials look like this, as a general rule. Exponential growth. And then the last piece here in the vocabulary, at least, to depreciate and appreciate is to go down, that's depreciate, or up, that's appreciate, in value. So sometimes, for example, maybe you have a Corvette and you bought it, it's a 1958 Corvette. And because that car is considered to be a collector's kind of car, you may have bought it when it was brand new in 1958 for $3,800. But now, because it's in mint condition and you've driven it very little, it might be worth $38,000. That car has appreciated, or in other words, gone up in value. Or maybe that same year, you bought a Ford truck, and that Ford truck was $1,500, and today it's worth $100 because that truck's value, which was not a collector's item, depreciated. It went down in value. So when it goes up, it's called appreciate. When it goes down, it's called depreciate. And just a little bit ago in the orange, we wrote down an exponential function look. And so here they talk about what does that in general look like. They write it down as y equals abx, where the x is the exponent. We would write it the way that you saw it before, so I'll just write it down one more time. Here's an example, y equals, and maybe you have something like a starting value of $1,000 or $100 that you put in the bank, and then maybe your base is 1.05, meaning you got 5%, and it would be to the x. So this is an example of an exponential equation. There's a starting value out in the front of the parentheses. The inside value tells you whether you're appreciating or depreciating. If it's a number that's larger than 1, then that means you're going up in value. If it's a number that's less than 1, it means you're going down. And you notice how the x is the exponent. And we'll be learning about how to do this in our calculator. I'm going to use an example. It says see page 238 for instructions, but I'm actually just going to write some numbers in. I want you to copy the numbers, and then we're going to talk about how this pertains to exponential growth. So first, I'll write them in the table. Second, I'm going to have you put the stage in list 1. and the number standing left in list number 2. So let's go with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is good enough, we don't need to really go any farther than that. And let's say that in our class, maybe we have, to begin with, 36 people standing. After one round and we roll the dice, we have 32 people, and then there's 28, and then there's 24, and then there's 22, and then there's 17, and then there's 15, and then there's 11, and then there's still 11 because nobody got out, the game that maybe we played, and then maybe 10 and 10. And what I would like you to do is I'd like you to enter those in list 1 and list 2 in your calculator, please. And then we're going to do something with it. Okay, so here in our calculator we see that we've entered in our 2 lists from our notes. And I want to show you something about these lists. So the thing I wanted to show you is that you can calculate an exponential graph from these. In the past, in Algebra 1, you probably have done something called linear regression, where you calculate a line of best fit based on some data points. We did it in here. And what we're going to do today is we're going to calculate instead this new equation, this y equals ab to the x thing. So I'm going to show you how to do that. You're going to go to Stat, and then arrow over to Calc. And then you're going to scroll down until you see EXP. And EXP stands for exponential. It's really nice that this calculator jumps so fast. So mine is a 0. And I hit enter. And then because you put things in list 1 and 2, it already knows that it wants you to talk about list number 1 and number 2. If you didn't put it in list 1 and 2, you'd have to say the list that you want. So for example, if you put it in 3 and 5, you do L3, L5. But we put it in list 1 and list 2. So then it writes some things down for us. It tells us that after they show this y equals ab to the x, that the a is equal to 36.25, and the b is equal to 0.866. Don't worry about the rest of the numbers that are up there right now. We're not going to talk about those today. So 0.866. Now this 36.25 supposedly is our starting value, but we actually already know our starting value. What was our starting value? 36. So that's off a little bit, but it's basing it on all the data that it collected. But I want to talk about this 0.866. So let me show you something about that. If I go back into my notes now, and they talk about how to find the ratio. The ratio is talking about how do you go from one number to another in your list number 2. For example, how did I go from 36 to 32? Oh, look, it looks like I subtracted 4. If we use that thinking, from 32 to 28, I subtracted 4, that's good. 28 to 24, I subtracted 4, that's good. But then from 24 to 22, 22 to 17, 17 to 15, that doesn't work. So it's not the same rule on average that I'm doing. And in an exponential growth and decay, or appreciating and depreciating, it's actually multiplying by number that's working. So the way that you find your ratio, and I'm going to tell you, is always take your second value and divide by your first value, and that's a good way to find your ratio. So what we're going to do right now is we're going to calculate that by going 32 divided by 36. Check that out, what you get. 0.8 repeating. I could also try a different set of numbers, like for example, if I didn't like that or I wasn't sure if that was the right one, I could also maybe do the second divided by the first. So I could also do 28 divided by 32 and see what that is. I'm guessing it's 0.8 something. 0.87? 5. So it looks like here, I mean, I'm somewhere around what we found in our calculator. Remember, we just typed it in and we found y when we did a b to the x, that the a was 36.25 and the b was 0.866. So these numbers are pretty close. This is 0.89 roughly, this is 0.88 roughly. The calculator is telling us that over time, the general idea is that it's going to be 0.866. So remember, the calculator uses all these algorithms to find the best fitting curve or line. So let's use theirs, just because. We know that in a recursive formula, we need to do a couple things. The first thing we need to do is we need to say where we're starting. So u0 from way back when is my very first number that I would get out, which would be a 36. And then if I wanted un, that's where we take that un minus 1, and we say what happens to everything that's going on. And based on what we see, we could have used in the red the 0.8 repeating for what's happening to the next numbers. We could have used the 0.875 for what's happened to the next numbers. Or we can trust our calculator to come up with the best number, which in this case is 0.866. And what that means is that for each subsequent number in my second list, which are my dependent values, on average, I'm going to be taking 0.866 times the previous number. Now, will that give you exactly the next number? Nope. But remember, this recursive equation, or any equation, is a prediction of what's going to happen. It's not what actually happened. That's the experiment up in purple. This brown is the prediction. So we do it based on what our calculator said. If you did put 36 here, that's probably the better one to put because we actually know the starting number. But I would have probably also accepted 36.25 because the calculator spit it out. The difference between this and what we usually use, like what the calculator spit out in orange, is that if we're writing something in an explicit formula, which means you're using a y equals, you would have written it this way. Y equals, and I'll use what the calculator gave me. 36.25 parentheses 0.866 parentheses to the x power. In step 3, it says, find the 8th term using this equation. So not what actually came out of my table, but let's go look in the calculator and see what happens.